Computers do not natively comprehend natural language. They require rigid mathematical translation. Human text is inherently nonlinear and high entropy, filled with typos and structural irregularities. This preparation functions as a deterministic mathematical translation layer, converting raw strings into a format algorithms can calculate. In any natural language processing architecture, this mandatory first step is called text preprocessing. The objective is to force chaotic string sequences into standardized, discrete mathematical units. We see that translation gap here: a raw HTML string with tags, inconsistent casing, and a URL sitting opposite a structured numerical tensor matrix. To cross this gap, the pipeline deploys a multi-step algorithm. It slices text, reduces morphological variance, and extracts syntactic metadata. Every step in this pipeline forces an engineering trade-off between maximizing computational efficiency and preserving critical semantic meaning. Without this rigid structural translation, downstream neural network models would process pure noise, rendering advanced AI calculations impossible. The process begins with tokenization, the physical fracturing of a continuous text string into foundational computational units, known as tokens. An algorithmic scanner inserts vertical slicing planes at whitespaces to isolate English text into distinct blocks. Vietnamese strings lack these explicit boundaries, requiring complex splitting. Finally, a regex scanner sweeps the English tokens, physically deleting HTML tags and URL blocks from the array. With noise purged, the system applies normalization for strict uniformity. The capitalized token block Apple algorithmically shifts characters to lowercase apple, matching the surrounding array. This lowercasing operation delivers a direct mathematical benefit. It drastically reduces the overall dimensionality of the system's required vocabulary dictionary. The array still contains stop words. These are high-frequency tokens that carry low intrinsic semantic value, such as the, is, or at. Standard engineering practice aggressively filters out these stop words to optimize processing speed and reduce computational load. This aggressive filtering, however, is a liability in specific analytical use cases, such as sentiment analysis models. Deleting structural words indiscriminately can inadvertently destroy critical semantic nuance and context. Tokenization and normalization successfully convert a chaotic string into a uniform, discrete array, but they fail entirely to account for the grammatical mutations of the words themselves. Natural language forces multiple grammatical permutations upon the exact same root concept. Efficient algorithms must compress these morphological variations into a single representative token to conserve system resources. The first and most rudimentary resolution methodology is known as stemming. We can see how stemming operates on the left side of this comparison table. It uses a brute force, heuristic-based set of rules to physically sever suffixes. The es suffix is chopped off the word studies, outputting the truncated string study. Stemming demands minimal computational overhead and executes with extreme processing speed. The critical flaw is that the algorithm frequently generates truncated, nonsensical tokens that lack valid linguistic meaning. Due to this inaccuracy, stemming is primarily restricted to rudimentary systems, like basic search engines, where semantic precision is optional. The more advanced, computationally expensive alternative is lemmatization. On the right side of the table, lemmatization uses a precision-based approach. By referencing dedicated dictionaries and grammatical rules, it deduces the true root. The token studies transforms into the valid root study, and the word mice morphs entirely into mouse. Lemmatization guarantees the final output is always a semantically valid word, explicitly known as a lemma. The specific engineering cost for this precision is significantly slower execution speeds and a heavy reliance on external database architectures. Despite the resource cost, lemmatization is an absolute requirement for high-fidelity tasks like chatbots or machine translation. By solving the morphological bottleneck, the pipeline standardizes the vocabulary entirely, clearing the way for the system to map structural relationships between the elements. The computational focus now shifts away from isolated tokens to the deeper syntactic structure of the complete sequence. The mathematical meaning of any single token changes drastically, depending on its grammatical function within a specific sentence. To solve this ambiguity, the pipeline introduces part-of-speech tagging, or POS tagging. Look at the isolated token book. A branching logic tree evaluates noun and verb paths, locking into a grammatical role based on adjacent tokens. This POS tagging applies broadly. Distinct structural labels, noun, verb, adjective, attach directly to each corresponding block in the array. This brings us to the final, most advanced layer of Phase 1 preprocessing, named entity recognition, or NER. NER is an extraction protocol for isolating high-value data points. The algorithm scans structurally tagged tokens, isolates the word apple, encompasses it in a distinct boundary box, and assigns a superseding label marked entity organization. Modern NLP systems fuse these POS tags and NER boundary boxes to construct a comprehensive multi-layered map of the original sentence. Utilizing POS tagging and NER, the pipeline has successfully extracted the hidden metadata required for a machine to parse complex human intent. Text preprocessing establishes a rigorous structural translation protocol, enforcing a strict mathematical schema on raw data. This high-speed visualization reveals the complete pipeline architecture. A chaotic web string enters on the left, flashes through sequential processing nodes, regex filtering, token slicing, morphological morphing, and metadata tagging, and instantly outputs as a perfectly aligned, structured data array. This sequential transformation successfully converts unpredictable human input into a highly organized, deterministic format. Achieving this rigidly structured baseline is the strict, unavoidable prerequisite for all subsequent neural network processing. With the dataset purified and mapped, the architecture is ready for projection into high-dimensional vector spaces, where tokens become coordinate-based neural representations.